Okay, third example, solving nonlinear systems. So we have y is equal to x squared minus 2x plus 3 and 2x minus y equals 2. Technically, this is ready for substitution. I could substitute this in here for y, but I'm going to go through the way I did it in the PowerPoint because that makes some students feel uncomfortable. So, you know, if I get the second equation, y by itself, and the reason why I'm not getting x by itself is because then I would end up with fractions. If I move the y and I divide by 2, I'd have to divide everybody by 2. And some students don't really care for fractions, and let's choose life anyway. Solving for y is easier. So I subtract the 2x, end up with a negative y. Remember, that means you have to divide everybody by -1. And then you end up with y is equal to 2x minus 2. And then if that's how you wanted to substitute it, now you could replace y over here with 2x minus 2 or vice versa. However, if you didn't mind and you wanted to just plug this x squared minus 2x plus 3 in here, that's fine, but you just have to remember that when you set it up, you have to put parentheses because you're subtracting all of y, and y is equal to this whole thing, x squared minus 2x plus 3. If you don't put the minus sign there, then you're not really subtracting what represents all of y. And then when you distribute that negative, you end up with 2x minus x squared plus 2x minus 3 equals 2. Combine your like terms, and you have negative x squared plus 4x minus 3 is equal to 2. Move the 2, that's negative x squared plus 4x minus 5 equals 0. Now let's just see what happens over here when I continue down the rabbit hole over here. So instinct should tell you have to get everything on one side because this is a polynomial. So I move the 2x and the negative 2 and subtract the 2x, add the 2 to both sides. And you end up with x squared minus 4x plus 5 equals 0, which is the exact opposite of this, meaning if I were to factor out a -1, I would end up with the exact same polynomial. And if I wanted to factor it and I loved myself, I would factor out this -1. And then I'm basically looking for two numbers that multiply to 5 and add up to -4 because I'm not about that life of doing the quadratic formula if I don't have to. So here we go. Oh wait, lies. This one does not work. There's nothing that multiplies to +5. I'll add up to -4. So I have no choice. I have to do the quadratic formula. So A is 1, B is -4, C is 5, and I just plugged in. Remember, it's negative B plus or minus B squared minus 4AC all over 2A. Make sure you draw that fraction bar all the way across. And when I follow the order of operations, okay, the double negative turns into a positive on the outside. I do the square, and then the product overall is negative, so it's a subtraction. I end up with -4 under the radical. So once you get a negative under the radical, you know that that means that you have an imaginary number. So we pull out the negative, that turns into an I, and the square root of 4 is 2. So we have 4 plus or minus 2i over 2. And remember, when you're reducing this, it's a holy trinity. Holy math trinity, you have to divide all 3. Or you could think about it as breaking it up. 4 divided by 2 plus or minus 2i divided by 2. Either way you slice it, you end up with 2 plus or minus I. So you have a complex solution. So what does that mean is happening in the graph? They're not intersecting at all. But that doesn't mean we can't find the solutions because the problem did not say solve the system and find all of the real solutions. It said it was just to solve. So that means you will not reject your complex solution. Now, don't be afraid. Just because x is equal to a complex number does not mean you can't find y. You would do the exact same thing that we did in the other two examples to find y. That's the beauty of math. You just follow the rules. You follow the same steps. So, just like before, I'm going to plug into one of the equations. But since I love myself, I'm going to choose that one, not the quadratic. Okay, not that it's impossible, but like I said, I love myself. Choose life. So now I'm going to plug in 2 plus I over here for x for this scenario. And then I'm going to plug in 2 minus I for x for that scenario. And I'm just going to follow the order of operations. Okay, so order of operations says I would add first, but I can't do that. So then multiplication comes next. So I distribute the 2. and I get 4 plus 2i minus 2. Then I combine these two like terms, the 4 and the negative 2, and I end up with 2 plus or minus 2i. So when I write the coordinates, it's 2 plus I, comma 2 plus 2i. And then on the other side, okay, I plug in here, that goes in there. And then order of operations says do parentheses first, can't do anything in there, so then multiplication goes next, distributed. And then we ended up with 4 minus 2i minus 2. These two are like terms, that's 2 minus 2i. And the coordinates. Now, one thing I want to caution against that I see students do is they do this. And this is super ambiguous because you don't know who the 2 plus I goes with. I mean, does the 2 plus I go with the 2 minus 2i, or does it go with the 2 plus 2i? So don't do that. No, don't do that. Okay. And then graphically, if I were to take a look at this, I'm anticipating that they don't intersect. And if I graph these two, there it is, they don't intersect.